the quadratic patterns again. So on all of these problems, first of all, one thing you're going to see is when you get the charts like this, you want to make sure that you check the first difference and make sure it isn't linear, because they eventually you'll get them all mixed up. And what happens is when I teach you the quadratics, you forget to look for linears, and you go back to the old problems and you can't do them because you just are trying to make them quadratic. So always check the first difference to make sure it is not a linear pattern. And you'll see that a little bit tonight on the review packet. So we're going to check the first difference each time. And so that's when you subtract here, and this goes up by 16. What's this go up by? 28.
40.
And then 40. So hopefully, I just made these up before you came in. Let's see if I made any mistakes. Now I'm going to, because the first difference is not constant, I have to keep going. So I'm going to check the second difference. And this one goes up by 12. And this goes up by 12. So I have a constant second difference. Okay? So that tells me it took two differences, which tells me that I have a multiplying pattern. This is a quadratic. And so instead of a linear rule here, we're going to have a linear rule times a linear rule. And that becomes a quadratic. Yes? How do you figure out the rule? How do you graph this? Oh, with the actual equation, you'll learn that in Algebra 2. And there's different strategies, actually. There's different ways to graph that. So what I'm going to do next is, now that I know I'm looking for two different rules, I'm going to take my numbers, like this number 4, and I'm going to figure out different ways to get 4 by multiplying. Because each one of these numbers that I'm multiplying, I want to get a rule here and a rule here, and it's based off of the factors of these numbers. So I could try, hold on, Ellie, 1 times 4 or 2 times 2. But rather than writing all the list out, kind of go with it and see, like, watch what I'm going to do. I'm going to just see if it goes with 1 times 4. Well, if I have a 1 here and I'm going to multiply by 4 here, I want something different over here, so I'm going to say, well, I could do 2 times what? 10. Okay, so maybe that's going to be helpful. So if I have a 1 here and a 2 here, then I'm going to try a 3. 16. And so now I have a 1, a 2, a 3, so I'm going to try a 4. And if you look here, 4 plus 6 is 10, 10 plus 6 is 16, 16 plus 6 is 22. So I have this multiplying pattern that is working for me, so I'm going to get rid of this. Allie, what was your question? Because you don't know if it's quadratic or linear.
You're in your head. But then why do you do second difference?
Because I might have made a mistake, or the book might have a mistake, or it's not a, like, and the reason I'm saying it would be a mistake is because right now the only two we're considering is linear and quadratic. Right. So if you were taking a test, I would always check, because if there is a mistake, you don't want to soak up 10 minutes of time looking for something that doesn't work. So it's sort of an insurance policy too. Okay, roll.
What about how every single one of those second numbers is multiple of 4?
10?
No, it's from 4. 4 is multiple of 4, 20 is multiple of 4, 48 is multiple of 4, 88.
Yeah.
So can you use that anyway?
You could. I think it might be more work than it's worth. So let's try not doing that and then looking back and see how that 4 shows up. So what I'm going to do is ask you to look at, let's say, the first term. So I'm going to go from 1 to 2 to 3 to 4, and I want a rule, because that goes up by a constant difference of 1, So that's the slope of a linear pattern. And so you're going to have a 1 right here. So I'm looking at just these numbers right here. And I'm trying to write a rule for them right here. Luke?
So what happens if it goes to a difference and then a difference and then a difference?
Then we are only, that wouldn't be quadratic.
It might be like
Okay. So it's just not part of this chapter. Stephen?
What do we like put a 1 before the end?
Well, I'm going to put a 1 before the end. Oops. Because just to remind you that that 1 had something to do with, there was a reason for the 1. No, I won't. Okay. And so then you take your 1, that's like your slope, and you're going to test it. So I'm going to do 1 times my n value, and my n value is 2. So 1 times 2 is 2, and my goal now is to get what's in the yellow circle. I got it. So I don't have to adjust this at all. I just leave this the same. I'm trying, so exactly. So a good way to think of that, Allie, is once I have the factors, I don't need to use these numbers anymore. I'm going to use the factors. Okay?
Whoa.
So now, Brendan,
Why is the next one?
oh, you know the next one? So the next one, we're going to look at, let's do it in green here. We're going to go from 4 to 10 to 16 to 22, right? So we're looking at these numbers in the green circles. And those are going up by how much, Brendan? 6. So, Stephen, that's kind of the question. That 6 plays a role. So that 6 goes here. Okay, so then I'm going to test it. So did you already do that, Stephen? Or Brendan? No? Okay, so what we do is we take 6 times n. So we're going to test it. So 6 times our n value. Here our n is 3. So 6 times 3 is 18. But I want 16, right? So I'm going to subtract 2.
So we use the n because that's what's on. Oh, does this work all the time?
This works all the time if you can find a multiplying pattern. There's a trick if you can't. Okay. Okay, so now we should check our answer. So let's just check it with 4. Okay? If n is equal to 4, the rule says I'm going to do 4 for the first set of parentheses times. I'm just going to pick 4, and my goal is, do I get 88?
Oh, okay.
I'm going to check it. Can you see the 88 still is there? 4 times, 6 times 4, right? Take away 2. So I'm plugging my n value of 4 into here and into there. So 4 times 24, take away 2. 4 times 22 is 88. And that's what we wanted, right? In the original problem, if you erase this, when n is 4, you get the value of 88. Does that make sense?
Yeah.
I got the -2, and then Josh, I'll take your question. Because I took the 6 here, right? That's 6. Becomes my slope over there, right? And then you take your 6, and you say, I'm going to test it. So I tested it. I could test it with 4, for example. So I would do 6 times 4, and I get 24. But remember here, I had changed this to 4 times 22, and I was trying to get 22. So from 24 to 22, I have to subtract 2. So you have to adjust. Josh.
So basically, we're just breaking it up into 2 linear equations.
That's exactly it. You're just doing 2 linears. That's why I kept saying you should really do the first night's homework. Because if you understand the first night's homework, this is going to be easier. And if you didn't do the first night's homework, there's a good chance you'd just be completely lost. Scott? So for a multiplying pattern, you have to look for factor pairs. Is that what you're saying? Like, get Oh yeah, we haven't gotten to the hard ones yet.
So if
These are the easy multiplying patterns.
And then you still didn't explain the dividing by two.
That's because it hasn't come up yet. So going back to your multiple of 4, it doesn't really show up here. So just because these are multiples of 4 doesn't mean that it's going to show up clearly in this equation. So just ignore it. Natalie?
So then what is the use of finding the first and the second?
Because the first difference, if it's constant, you know it's a linear pattern, so you don't go through all of this.
Well, but if you can find a second, then you
Okay, you can see that, but what I'm saying is, it's your choice. You can choose to listen to me or not, but I'm saying that there are mistakes. Sometimes I make a packet up, I could have made a mistake. Or you're taking a test, you could have made a mistake, or the book sometimes has mistakes, so it would save you a lot of time if you found out that there was no first or second difference. Then you'd say, are you sure this is right? Otherwise, you can spend 20 minutes looking for something that doesn't exist.
That makes sense.
Yes, it does. Brendan.
So what was the first parenthesis for?
Let's do another one and see if that answers your question, and then we can go back and look at it. Okay, so we're going to go through the first difference again. So the first difference here is 10, and then it's what? 28?
No.
18, right? Yeah. 18. Okay, and then should be 26, right?
Right.
It is.
And it is. So the second difference is 8. 8. So there is a second difference that's constant. So you're done. Your job is done. That information is now used. So cross it out. Okay. What that tells you is you have a multiplying pattern. We're going to look for a rule that shows that multiplying pattern. So the next thing we're going to do is we're going to do factor pairs. That's right. So we're going to look for factor pairs. So 2 is like 1 times 2. Okay, 2 times 6, let's try that. That would have to work, right? 4 times 14.
Wow.
So that's a clear multiplying pattern, right? Oh, thank you. Okay, got it? So we're going to go for, so now, by the way, once we have that multiplying pattern, we're not going to use these numbers anymore. Because we have 30 written as 3 times 10. We're going to look at the pairs. That's why I keep crossing things out. So now I'm going to take the 1 and the 2 and the 3 and the 4. You guys probably just see this one, right? It's just 1 n, right? Because the difference is 1. And these numbers match the n value, right? So it's just n. That's the whole thing. Connor.
I know what it is.
Okay, what is it?
It's n over n minus 2.
Well, let's check it. So he says it's 4n minus 2.
He's right.
He is correct.
Okay, for those of you guys that aren't sure yet, do you see the 4n? Because your differences here are 4 from 2 to 6 is an increase of 4. From 6 to 10 is an increase of 4. And from 10 to 14 is an increase of 4. Right?
Right.
So the 4 is here. Then you check it with one of your terms. So 4 times 4 is 16, but I need to get all the way down to 14. So I have to subtract 2. You got it. Okay, raise your hand if you get this. The easy ones. What do you multiply these differences by? The 4? You multiply by n. You always multiply by your n value, your slope. And then you go over and test it. So like I was going to test it with 4, but I could test it with 3 now. So I'm going to say 4 times my n value is 3. That's 12, but I need to get to 10. So I have to subtract 2. And then in this one here, since there's no add or subtract, you could just rewrite it as n outside of the parentheses. So that's a nice way to write your final answer. And then if I asked you to find like the 500th term, you know, if I say what's the value when n is 500, hopefully you're not going to work it out till 500, you're going to use your rule, right? It's going to be 500 times what?
100 times 2,000 minus 2.
So 1,998, and you'd figure that out. Because the other day somebody was saying in the handshake problem, well, I can figure it out, but I can't come up with a rule. So if I said, what if there was 90 people in the room, how many handshakes takes place, you're going to want to know the rule, right? Okay. So we're going back to the handshake problem. This is where the problems get harder. And even though I have polygons here, these are the same things. You'll see that these numbers are the same as the handshake problem, because if I, you know, let's see, had people here, right? There's little people. Those 2 people can make 1 handshake, right? And if there's 3 people, 3 handshakes, and if there's 4 people,
6 handshakes.
6, right? So we have to add those in. They can shake, and they can shake. So the vertices just represent the people. And so if there's 5 people, then there's all of the diagonals that are already there. And then there's 7, 8, 9, 10, 11. Oh no, 6. I started counting wrong. There's 5 in the inside and 5 on the outside. I skipped the number 6. Okay. And then for this one, there's 1, 2, 3, 4, 5, 6, 7, 8, 9,
You have to do this on your own.
and then the 6 around the outside, right? So there's 15 when there are 6 people. Okay? So that's what you guys did for like a warm-up the other day. So this is 3, what's this? 4 people. 6 handshakes, 5 people, 10. And if there were 6 people, 15. Okay, so now Stephen already figured it out by just, you know, observing patterns. But now we can go back and realize all of the stuff we were just talking about. This hasn't, we can check the first difference here. And this goes up by 2, and then 3, and then 4, and then 5. So we know it's not linear. Then we can check the second difference. That goes up by 1s. So we know it's quadratic, which tells me that there's going to be a multiplying pattern here. And we have to figure out what that multiplying pattern is. So we're not going to use these numbers now, and we're not going to use these because that helped us figure out the multiplying pattern, that there's a multiplying pattern. But here's where it gets tricky. When I try to figure out So when I try to figure out a multiplying pattern for these numbers, I'm going to run into trouble. So think about ways to get 1. How do you get 1 with multiplying? There's only one way, right? 1 times 1. But how do you get 3?
1 times 3.
Right, or 3 times 1, right? But if I try to follow this pattern, 1, 3, this would have to be a 5, but I'm trying to get 4. So if I switch it around and say, what about 1 times 3?
1 times 4? 1, 1, 1.
Right, so if I do this, I get 1 times 1, 1 times 3, you could argue this is a pattern, 1 times 4. But the thing is I'm stuck right back with the same numbers, or 1 times 6. Like I'm not making any progress, in other words. Can you see there's like not a clear pattern here? But what I'm saying is, can you see that it's harder to find a multiplying pattern here? You know, like on the other one, if we look at the other page, when you looked at the multiplying patterns, you had 1 times 2, and then 2 times 6, 3 times 10. There was a pattern where the numbers formed a linear pattern, and this doesn't do that. Stephen, do you remember what was different about your rule compared to everything else we've done so far? Does anybody remember?
Yeah, so
It was divided by 2. Opposite divided by 2. Right, so we learned that in this rule there was a divided by 2. So the trick is, if you can't find a rule, you could just take all of your values and double them. And try to find a rule for the doubled ones. So I'm going to double each of these. So I'm going to double 1 and I get 2. I'm going to double 3 and I get 6. I'm going to double 6 and I get 12, 20, 30. And if that works, I'm going to take my answer and undo it by dividing by 2.
Now it works.
So it takes a couple tries, guys. So let's see if I can find a pattern for this. So 1 times 2. What about 6? 2 times 3. 3 times 4. 4 times 5. 5 times 6. So do we agree there's a pattern?
Yes.
So then you're going to not use these now.
What if there wasn't a pattern?
Yeah, there probably will be. I mean, so the whole idea of this unit is to teach you a skill that works when it's appropriate. And if none of these skills work, you would go to other strategies, which is what you would learn in Algebra 2. You'll learn a whole bunch of other strategies. So this is it for this year. So it's either linear or quadratic. And you can either do quadratic the first time with the multiplying pattern, or you can double, and you'll find a pattern. And if none of that works, this becomes a problem in a more advanced class next year. Okay? So now we're going to take the first number. And one thing that I have to really caution you about, you have to be really careful about your work, because if you are like me, sometimes you can get sloppy, and you want to make sure these pairs stay with the original n value. So you might want to lengthen out your table so they don't get associated with the wrong n value, you know, if they move across the bottom of your paper. So they should still be with the original n value. Like, for example, this 6 here is associated with the original n of 3. So try to be neat. So now I'm going to take my 1, 2, 3, 4, 5. I have to go all the way back to the original n value right here. So it goes up by 1. Do I have to adjust it at all? So this is an n, right? So if I test it, 1 times 6 is 6. I'm trying to get a 5. Minus 1. You have to go all the way back to the ends to test it. Okay, so now I'm gonna take the second set and go from 2 to 3 to 4 to 5 to 6. Those are also going up by 1, right? So I still have an n here, but when I test it, like n 1 times 5, I get 5, and I'm looking for 5. So I don't need to adjust it. So the answer is n times n minus 1 over 2. That's it.
So is it just the same thing to be multiplied?
It's the same, so let's check it. So if I check it for 5, if I check it for 5, it'd be 5 times 4 divided by 2, which is 10, right? And the Pentagon, right here, had 10 diagonals, right? Which represents the 10 handshakes.
Wait, so why wouldn't you like distribute it? So it'd be like n squared?
You don't have to. It's easier to test it if you don't distribute it. I would leave it in factor form. It's not incorrect, n squared minus n over 2, but it's so much easier for me to just do,
Well, yeah, it's really easier for you
to check it. So they're both correct. Okay, so the homework. Okay, so let's just try a couple of homework ones, like problem 3. What's it say? Okay, so the question is about diagonals from one vertex, right? So even though they don't give you a table, you can set a table up. So just draw a table, approach all of these with a table. And you don't need to set up a fancy table, just use the lines on your binder paper. But remember also that you have, you're going to want a couple of values to get your table started. You don't need tons. But they talk about a 35-sided polygon, right?
Yeah.
Is that what they? Yeah. So you're not going to actually do that. You're going to get your rule, and then you're going to put your rule here, and you're going to put 35 here. Oh, I hope you didn't draw a 35-sided polygon. Okay. So Sky, always in problems like this, you're going to solve a small. Okay, so let's do figure. The next figure. The figure and the diagonals, right? So watch how I would do it. First-sided polygon has 3 sides, right? So if you have a 3-sided polygon, there's no diagonals from one vertex. So then you would go to a 4-sided. So it's different than the last picture we had up. From one vertex, there's only one diagonal. Do you agree? Okay. If we had a 5-sided polygon, from this vertex, there's 1, 2. So if you think that that's not enough of a pattern, yeah, but you don't want to do that. Right? So put another one in just to make sure. Put it 6, draw a hexagon. And then from one vertex, there's 3, right? Got that? Okay, so you've got your picture. Let's you catching those letters. Let's move that for a minute. Hey, they're stuck together, that's why. But the pictures have served the purpose, right? So I can erase them. Okay, so I'm never going to draw a 35-sided polygon. Yeah, Josh. There's a place for you to do this in your packet. It's problem 3 on page 115. So this is page 115, problem 3.
we actually have to be doing homework for patterns, like for.
You could do it on binder
Yeah,
paper.
because Wednesday's night homework, I did it all on.
So right away, I'm going to look at the first differences, and they're constant, right? So look how much work you did for this. Because this is just going to be 1 n, right? And then 1 times 4 is 4, but I need a 1. So I just subtract 3. So this should be 32. So this is in the section with multiplying patterns, but it's not a multiplying pattern. So you definitely want to check because they might be easy. Roll it.
It says that we have to draw the next figure.
Right?
We actually have to do that?
Yes, you actually have to do it.
Okay.
It gets your brain warm up when you draw those pictures. It helps you like connect.
So it's the next figure.
That's what it says, the next figure. Right. You never want to draw something giant. Natalie.
So, Emily came up to me and said that we didn't have to do that.
And I sent an email home saying the same thing.
It was an email.
Because I was kind of worried that it
That's why I'm trying to help you start it. Okay. So let's try the next one, right? Let's try number 4. Number 4, you guys, look at the question on number 4. It says, what are the total diagonals? Not just from one vertex, but the total diagonals in a 35-sided polygon. So, Sky, did you draw that one? Oh my goodness. Okay, but this is what I want you to think about. Did we already draw a picture like this somewhere? Isn't that the handshake problem? Boys, isn't it the handshake problem? Wait a minute. But if I want to figure out the total diagonals, isn't that really the same thing? Except for, you're right. In other words, the pictures are there, but we might not start with 1. We might just start with 3, right? Because the first polygon is a triangle. So this could be figure, and this could be diagonals. So our first figure is going to be a triangle, and there's no diagonals there. Our second figure is going to be a quadrilateral, and now there's 2 diagonals. So the next figure is a pentagon, and there's 5 diagonals, right? So it's a little bit different problem, but we can still use that picture. You don't want to keep drawing the same picture if you just drew it. And so for 6-sided figure, there is 9. So the picture served its purpose. Does that make sense, you guys? Okay, so then we just are going to get rid of this. We already know a lot about this pattern. Do I know if it's quadratic or not? It is quadratic. How come you know that, Ben?
Because they don't have a constant.
They don't have a constant difference, right? This is going up by 2. This is going up by 3. That's going up by 4. And the next time, they're going up by 1. Is there a multiplying pattern?
Yeah.
I would always ignore 0 and look for a multiplying pattern somewhere else. So like, how do you get 2? 1 times 2. How about 5? 1 times 5. Is anybody noticing something when you have 2 primes next to each other? You've got to double it because you're never going to get anything different than what you start with. Isn't that a good rule? So right away, I'm going to take my lines and extend them so I don't get lost in my work. So I'm going to double everything. So the other thing I'm going to do is I'm going to now get rid of this because this information's already served its purpose. And I'm going to get rid of these because I'm going to double them. So instead of 2, I'm going to have what? 4, 10, 18. Now I'm going to look for a multiplying pattern. Any ideas?
Oh, 1 times 4.
1 times 4, 2 times 5. And then also I need to remember that I not only have a multiplying pattern, but I doubled, so what do I have to do over here? Divide by 2. Okay, do you guys see a pattern from 1 to 2 to 3? It goes up by 1.
The next one goes up by 1.
And when I do 1 times 4, I get 4. But I really need a 1. So what do I have to do? Subtract 3. Now do this one. This goes up by what? 1. And when I do 1 times 6, I get 6. And I want to 6. So I leave it the same because I got the 3 for the first pattern. So my answer is n times n minus 3 divided by 2. That help?
Yeah.
Okay.